My name is Diego Oppenheimer. I've been in the data analytics field my entire career. Started Algorithmia about 5 years ago. Before that, I was building products at Microsoft, including Power BI, SQL Server, and Excel. So dealing with kind of like what does it look like as analytics start becoming a more important part of our everyday life. So the goal of today's talk is to talk a little bit about what actually happens once you've actually trained a machine learning model or a data science model, and how do you operationalize it, and what does that look like for organizations who are starting to adapt this kind of software into this kind of workload into their software. So I'm going to start out with, for those of you who are not familiar with a pretty good paper that was published by Google a couple of years ago, and it's called The Hidden Technical Debt in Machine Learning Systems. And the gist of it is really that the actual ML code is really one of the smallest parts of the problem of when you're actually looking at a machine learning system. The infrastructure around configuration, data collection, data verification, feature extraction, process management tools. How do you serve the infrastructure of these models at scale? How do you monitor these models at scale? Ends up actually becoming the biggest part of the workload. But if we think about how data science teams are composed today, and actually those workflows, we're actually grabbing data scientists in a lot of cases, asking them to manage their own infrastructure, actually go build out their own infrastructure, manage their own data systems, and build out from that. And so what you see is a pretty high risk of people who are actually really specific and extremely important to actually developing this ML code, dealing with a whole lot of operative pieces that they might not be the best suited for. And so I highly recommend reading this paper. It probably won't put you to sleep, but it is an academic paper after all. So last year, Algorithmia actually surveyed over 500 data scientists and machine learning engineers across the industry in large organizations. And we actually found that the great majority of data scientists are actually spending most of their time and doing really everything except data science. So when we were actually, almost 75% of the time was actually manual infrastructure work that was nothing to do with the actual code, the analytics, and the science that they were actually building. And when we actually dug a little bit deeper into that, we saw that about 30% of the time was actually building ML tooling, 30% of the time was actually managing their work. How do I do reproducibility? How do I actually keep versioning? Where did that data source come from? Am I allowed to use that data source? And then the lion's share, about 38%, was actually deployment. And so we've actually heard this story where it's like, it took me a week to build this model and 6 months to deploy it over and over again across the industry. So just quick show of hands here. How many people in the room consider themselves data scientists? Great. Machine learning engineers? Infrastructure DevOps? Fantastic, great. This is a perfect mix. And management, for all that, project management, PM, excellent, great. So there's gonna be a little bit for everybody today. We're gonna try to make a happy medium where everybody's gonna be happy with each other's jobs and start talking to each other around that. And that's really what I'm gonna talk about. So the core of it is that we've actually understood the normal software development lifecycle for quite a long time. It's something that we've developed over the years. We understand how we do deployment and monitoring and building of applications, how unit tests are done, how we actually can expand on giving permissions, deploying to different kinds of applications. And a lot of this can actually be used back in the world of machine learning and data science. And so it's usually about talking about how do we think about these new applications in the world that have these analytics, and can we apply these same principles from the software development lifecycle? So the core difference, right? If we actually look at a traditional DevOps kind of workload, there's a create the application, build, test, deploy, monitor, rinse, repeat once a week, once a month, once every 6 months, once every 5 years. Really depends on the time frame that you have, but this is kind of what it looks like. When you start looking at the ML lifecycle, it's really data prep, and then there's train, deploy, manage, train, deploy, manage. This could be happening multiple times an hour. This could be happening multiple times a day, multiple times a week. The actual iteration pace is actually much, much higher. And so when we start thinking about how our traditional systems are orchestrated, we have to understand the speed of redeployment and managing that is necessary to be able to do this automatically. And the core of it comes out, at the end of the day, it's just code, right? But the core difference, if you're gonna remember something today, is that in a traditional DevOps environment, we're dealing with actually deterministic code. And when we're working with predictive analytics, we're looking at probabilistic code. So code that even though we do nothing, it changes because the data changed or it drifted in one way or the other, and we actually have to pay attention to that. So a lot of the differences from the traditional software development lifecycle come to fruit on the fact that this is, the kind of the core principle that this code, you can do nothing changes, and just the data moving in one way or other, the behavior is going to be wildly different, and we have to monitor for it. So when we look at the ML lifecycle, right? Data, train, deploy, manage. So let's talk about the data systems. So the data systems in tradition, so how many data engineers here? Excellent, right? So these are the people who've been spending laboriously the last couple of years, maybe a decade, actually, moving from what was like traditional databases and DBAs to actually systems that update and record each other and build ETL pipelines and extract the features that are needed and clean up the data warehouses and feed into the data lakes that the actual machine learning and data scientists can actually use. So then you move it, and so this is extremely important. These data systems in almost every organization, by the time a data scientist shows up, these systems already exist, right? So like, and if you are a data scientist who showed up to an organization and these systems don't exist, warning, right? It means that you're not gonna have data to work with, which is, as you know, really big problem. So when you move away from that, once you assume that the data systems are working and you actually have the access to this data that you can actually use for training and building your models, we start going to the world of actually training, which is you're querying the data from these systems and you're actually building training. And in every single large organization, very similar to how you see IDEs in a large organization, there's all sorts of tools. Right? And so, there's a strong desire to standardize, hey, we're going to do everything in TensorFlow. We're going to do everything with Python and scikit-learn. And that's worked just about the same as it's worked going into an organization being like, we're only writing code in Python and nobody can write code in anything else. It doesn't, right? And we have about 30 years of experience to look back and see that. So there's this natural progression around data scientists are going to bring the tools that they're comfortable with. That might be R and certain statistical packages, Python and their packages. They might be really in love with their particular cloud provider solution. But the fact is that multiple solutions for training are going to exist, and they're going to be going and pulling from the data management systems the data that they need to train. So this is great. Now I've iterated, I've tested, I've validated my model, I've secured like how it's behaving, I'm comfortable. We're ready to make this business impact, right? We're ready to put this into production. So what's next? So the next is now we actually need to move it into production. The lucky teams, the lucky data science teams have DevOps and software architecture teams embedded in them, working with them to actually grab their models, productionize them, run them at scale, help them go through that. These are the teams that actually understand the requirements from the enterprise around security, backup, audit, scale, things that usually data scientists are not really thinking about when they're just trying to say, hey, I just want a more accurate model for whatever it is that I'm calculating. So when we have to think about once this model needs to move into production, it's not just slapping an API around it and saying, good luck, right? And seeing what it is. We're talking about how are we going to connect to the data sources that we need to go score on? How are we going to ingest models from a whole various set of different tooling? How are we going to make them discoverable? Right? At the end of the day, if the applications are the ones that are going to be consuming these models, how are they going to discover that? And then how are they going to actually call it? If I already have a web application that's written in C#, just because I built my Python model and my model in Python, they're not going to go rewrite the entire website or anything. So you're going to have that interface, the SDK, the REST APIs available for that abstraction. You need dependencies. In a lot of cases, a lot of these models to run need a whole sorts of libraries and dependencies. How do you move those dependencies from the training system over to the deployment system? In the best case scenario, they just work. In the worst case scenario, they're not even approved to go into production. You have all sorts of dependencies that are not allowed by your organizational structure. And what do you do at that point? You have to maintain the SDKs for the integration with those applications. You have to be able to serve those models at scale in different kinds of infrastructure. So we start hearing a lot about this, especially large organizations, especially in financial services, we hear this a lot, the 3-1 model or the 2-1 model, 2 clouds, 1 on-premises. And what that means is that they're trying to solve what they're building so that it works exactly the same on their 2 preferred cloud providers as well as their on-premises location. So now you're actually thinking, okay, I'm the DevOps team, I'm the infrastructure team, I'm going to have these models coming into me, and I have to solve it for 2 clouds, potentially on premises, and it always has to work the same. So you can, and then on top of all of this, how do I monitor and log the security of all of this? So especially regulated industries, who called what, when, with what data, what time, and why is extremely important. In the some cases just for your own information, and the worst cases because you have to give this over to a regulator when you made a decision around it. So these are all the considerations that now have to be part of this new life cycle once you're starting to use these predictive analytics inside your real world applications. So I'm going to talk through a couple of the challenges that exist that need to be taken into consideration when you're actually building this automation and CI/CD process for your organization. So the first challenge is heterogeneity. So I talked a little bit about it, but especially in data science, the amount of tools in different languages and combinations is exploding on a daily basis. We see this all the time. New library in NLP, I loved it, but it's only in R. Okay, but I need to actually call that with a pre-classifier in Python. Oh, great. Okay, but I want to actually train a model in PyTorch, and I want that to run on GPUs because I've seen that the inference on those GPUs is a lot quicker. This now, when you start to think about it from a systematic problem, and also in the fact that you're not going to customize this for every single time you're deploying a model, how are you going to actually solve this in a general way becomes extremely important. So what you want to do is you're going to assume that you're going to have a whole bunch of different frameworks that exist and that they're going to be combined in all sorts of different ways. So your infrastructure, your CI/CD process and your deployment infrastructure has to be generic enough to be able to accept all of these inputs and work with them in a proper way. A lot of times, these combinations also require snapshots. So if you think about, hey, I trained in the environment, great. And I'm sure a bunch of the DevOps people in this room this will resonate with them. So the data scientists grabbed their libraries and they built it and then say, hey, don't worry, I put everything in a Docker container and you can actually go deploy this. Great, that Docker container is 50 gigs. It's how do I actually deploy that? Right? How do I actually deploy that at scale? You've literally added every library on earth into this Docker container. So actually putting some sort of actual controls around what you're actually putting into these containers so that they actually quickly can be scaled out and in a reasonable way. Because again, this isn't malice of the data scientists. They're just working with the tools that they understand. Oops, wrong way. So next challenge, composability. Models don't exist in isolation. Models exist in pipelines, right? So this becomes an extremely important thing, especially when you're considering how you're deploying models at scale. So usually what you'll see is a pre-processing function, maybe another pre-processing function, maybe a feature extraction, then a classifier, going into another classifier, maybe going into a scoring. And so think about it, every single one of these in different languages, in different libraries, with different components, and they all need to exist in your production environment. So thinking that you're going to have these multiple languages, multiple frameworks becomes really important. So in this particular case, I try to illustrate it in a really basic use case. If you think about it, so scanned documents are going in. I'm doing text to OCR with an R-based workflow. I'm doing a language identification with scikit-learn and Python. If it's in English, I'm going to go directly to my text vectorizer and then to my sentiment analysis. If it's not in English, I'm going to try to translate it into English so then I can do it into my... And so this is actually a really common pipeline for document extraction that gets built. And there's already here 5 different languages involved, multiple different kinds of hardware, multiple different kinds of framework, and all of this needs to be managed in an easy way. Now think about that first slide that I showed you where there's iteration and republishing. If that's happening multiple times an hour, what DevOps team can actually keep up with that? It's pretty much impossible. This is why you start seeing that it takes 6, 9, 10 months to be able to deploy anything in production. And by the time you got to that, the whole pipelines are really essentially stale because you have to start over again. So this is kind of thinking about how you're actually going to do this at scale is really important when you're designing your system. So another challenge, performance, cold starts, throughput. So with traditional apps, performance is usually pretty easy to define. More data, faster throughput, less latency. Those are execution-based metrics. With machine learning data science workflows, it's actually far more multidimensional, integrating several different kinds of metrics. You have to integrate vectors like accuracy, sensitivity, specificity, precision. So for example, if you want to do real-time fraud scoring, you might need latency requirements of under 30 milliseconds. And you might be willing to live with some false negatives to do that. So I usually I like taking the example of anybody here been and like swiped their credit card at that kind of sketchy gas station in the middle of nowhere and got an alert 3 hours later from your credit card saying, hey, did you do this? 3 hours later, right? It's because that's batch scoring that's happening way, way later. And so again, the ideal would be, could we actually do that in real time? How do we design the system so that we could actually do that in real time? If you're using a similar model to do forensic analysis, you might not care how long it takes. It's a batch job that runs overnight, but actually you really, really care about high accuracy. So being able to actually make up and say, I will take less accuracy for higher speed or slower speed for higher accuracy is a business decision. It has nothing to do with the actual infrastructure at that point. But those are the things that you have to be able to make those decisions around the models that you want to use. Keep on hitting the wrong button. Another challenge is lack of reusability. And this is the one that's actually kind of like the scariest. And so I usually go, and when I talk to data scientists, I ask them, it's like, how many times have you rewritten the same pre-processing function? And I always get the same chuckle. It's like, well, every time. It's like, why? Right? So if we start thinking about the different functions, about the different extractors, about the different mappers that we use in our different workloads, if we could actually publish those once and then just reuse them always, so essentially treat them as their own microservices, this now gives the entire organization much higher speed. The fact is that most of you working in enterprises, you're working with some of the same data, you're working with some of the same use cases, and you're just kind of giving it different flavors. So actually thinking reusability in the same way that we think about reusable services in traditional software development is extremely important. So you don't want teams consistently reinventing the wheel. You want models and other assets to exist not only on laptops or on local servers, but that is shareable across your entire organization. And you want, you don't want multiple languages and frameworks that are going to introduce incompatibility. So, one of the ways to doing this is by actually having these services, have them once, have them updated by a team, and then be able to use them of that. I was talking to a media company a couple of months back, and they had a whole image classification pipeline. And the first step, right, was actually grabbing the images and resizing them to a specific size so that they could just reducing the size of the image for a standard so they could do the classification. And I was like, okay, great. He's like, yeah, it's really terrible because we have 10 of these implementations across the organization. And every single time we need to patch, security, we have to go chase around 10 different implementations of the exact same pipeline because different teams are using it. That's a disaster. That's just a disaster waiting to happen. It's also a huge waste of time of everybody involved. So thinking about that reusability becomes extremely important. The next challenge is iteration speed. So, and this is really about, so the data science team is the fastest moving team in software, just by nature of how it works. Right? So data scientists are tasked with iterating, right? Like iterating, experimenting. By definition of what they do in their role, they are the fastest moving team in software. And so we can't stop that because the iterations increase accuracy, the iterations allow for better outcomes. And so this actually happens at a much faster pace than any of the traditional software we've seen. And so new features, bug fixes, performance enhancements also happen at that speed. So in machine learning, the output is an evolving ecosystem, inference made by the interaction of your code models with live, often unpredictable data. So interactions, the new data can introduce model drift that affect accuracy, requires constant model tuning and retraining. So this is why it becomes super important to create the CI/CD pipelines because there's the assumption that the deployment is going to be continuous, always happening because that data is going to be changing the code. So as a result, ML iterations are much faster and much more frequent than traditional app development workflows. This actually places greater demands on versioning and operational processes and requires a greater degree of agility from your DevOps staff. So when you're actually grabbing a team and saying, okay, we're going to borrow a DevOps resource to help us productionize this, I don't think they understand that they're signing up to do this 14 times a day, right? And so building that pipeline, building that iteration becomes extremely important. Another one is, and this is one that I try to really, really hammer on, training and production infrastructure is really different. And people like to think about, hey, this is my machine learning platform, but if you really dig into it, these are two completely different paradigms from a computational perspective. So if you think about training is long compute cycles, It's a fixed load usually, so you can scale up the infrastructure because you need a lot of GPUs, but the actual training load is actually fixed in most cases. It's stateful, obviously, you have to change this, and it's usually a single user. So usually some person is actually going out and executing a job and running an experiment or a group and doing that. On the flip side of that, if you're looking at production, right, we're actually looking at short, really intense bursts of compute, calculations, inferences around what you're calculating, completely elastic. So as volume goes up and down, you might have an extremely busy hour in the day that needs hundreds of machines, and then the rest of the day is completely flat. It's stateless. My predictions are completely irrelevant from your predictions because we have a new set of data coming in from that. And it's multi-user, right? You think about a model that's getting called from, a fraud model that's getting called for maybe, hundreds of thousands of mobile apps every single time there's a credit card transaction or something like that. So we're dealing with a completely different paradigm from an architecture perspective. So thinking about choosing the right architecture and the right deployment for your training stack as well as your production stack becomes really important as well. Another challenge is auditability and governance. And so we call this problem the who called what, when, with what data, and at what time. So in regulated industries, we can call pharmaceutical industry, it's called pharmaceutical, in finance as well. So in pharma, if you're using, and they are, right? If you're using kind of machine learning to do drug discovery, at any given time, the FDA can come in and say, okay, you're using this for drug discovery, show me the entire lineage. Where did the data come from? How you transform that data? What did you use for training? And then when you actually did the scoring and the actual inference, every single result that you gave, you have to be able to package this up and give it to the FDA if they request it. In financial services, exact same thing. If you're actually rejecting a loan, at any given time, you have to be able to come back and say, hey, who called what data at what time, why this decision was made. The use cases go on, but the core of it is that we are actually required now to understand not only why the decisions were made, but definitely trace what decisions were made at any given time and be able to provide that. So your system of deploying machine learning in production has to have the audit and governance controls required for you to be able to do that. And then evaluations and modular dependencies. So we've talked about, A/B testing A/B testing is something that happens all the time, green, blue, in normal software development. Now we're in a world where we do A, B, C, D, E testing. We're trying multiple models against the same problem. We're doing challenger problems where we're saying, okay, which is the model that's actually behaving the best in this case? And then that's the one I want to put in, put forward. I have to be able to understand what every version of the model was calling, what the precision was there. If I just pushed a new model and it's calculating twice as fast, but I've lost 30% accuracy, is that acceptable? Maybe, right? That's a business decision at the end of the day. So being able to actually evaluate all the versions, have that semantic versioning, and be able to run them at the same time becomes extremely important. So it's not only important for your CI/CD system for ML can deploy this version, you have to be able to deploy all the previous versions in an instant as well, so that you can actually run these tests against each other. And then one of the things that I talk about, now imagine the dependency management, right? So it's fairly easy in a traditional DevOps. I have a set of dependencies, I built my application, I deployed it, I know it's working, now I monitor it. Now I have new models going in, and maybe we added a new stat library, right? Maybe we added a new cleaner. Maybe the stat library actually got updated under us, right? And we didn't even realize that. And now the calculations are being somewhat different. So being able to track all of that version to version at the same speed of iteration becomes extremely important. So how do you build the framework around that is extremely important. And then finally, another solution around this is really API endpoints and model repository. This is really where we want to think about abstraction. Machine learning models are only good if they can be consumed. I know this is not rocket science, but it's real. Sometimes we forget this, right? If an application can't consume it, then they're no good. But the application's not going to change for the machine learning model. They're not going to go rewrite the website. They're not going to go rewrite the iOS app. They're not going to go rewrite so you have to actually make sure that you can abstract the machine learning models and data science models so they can be called from the application and you can meet the application there. Another one is, how do you approach the repeatability? Make it searchable. So we make data assets searchable, in an organization. We make code searchable, we make repositories searchable. Make your model searchable as well. Inside an organization, every single model should go be registered and be part of a model repository. I should easily be able to search before I even start building a pre-processing function and then see if I can actually consume it. Documentation, code snippets, and the resources and the history and the markdown of that model should be available at that time. So if I'm actually an application developer and saying, hey, I'm going to go consume this model, I should be able to understand its entire history. I should be able to understand what it's come from, what it's good for, what it's bad for, and what it's used. And that should be at that time. And then obviously important, integrating with your role access-based controls. In some cases, again, especially regulated industries, what I can see, you're not allowed to see. What they can see, I'm not allowed to see. And so being able to actually tie your organizational architecture into how you actually make available these models and access to those models becomes extremely important. And then finally, as I said, another solution, model versioning. Again, just like we version code, you have to be versioning models. You want to maintain backwards compatibility for all models and every model. Again, either if it's just for replaying, in the case of a regulatory thing, you need to replay a run. But in most cases, it's a good practice, just keep track of all these models in backward compatibility. You want to enforce semantic versioning, standards to reflect model changes. You want to version all the associated metadata. Within. So one thing that we push big at Algorithmia is like Git-based workflows. Why aren't, data scientists should be able to use Git-based workflows just as much as software development. And this is a solved problem. Software developers have been doing this for years, and we should be able to do this in data science because it actually works. And then you want to build standard architecture, as I said, around Git. Finally, really around the compute efficiency. So traditional capacity planning is extremely wasteful and expensive. It has hard capacity limits. You're paying for a lot of access. If you're doing like local maximum planning, so kind of like auto scaling in the same way that you see today in traditional cloud providers, where they will scale by machines, it's a little bit more efficient, but there's still a lot of inefficiency. Using serverless technology to run your models, both on CPUs and GPUs, is actually the maximum efficiency boost that you can get, and using the resources under there in the most efficient way. It's substantially lower cost, and it actually provides infinite scalability, assuming you either have on-premises, the capacity for it, or in the cloud provider, there's a cost associated with it, but you can get all at once. And then finally, as you're building these deployment platforms, as you actually deploying your management platform, you want to be able to do chargebacks and attribution. So who called what, when, at what time for audit and governance, but also to be able to like, hey, there's compute involved here. Sometimes really expensive compute. We have customers that use our platform with, like 80, 90 GPU machines at a time when they're actually scaling, but there's a shared resource across multiple parts of the organization. So being able to build the different parts of the organization that are actually using that compute becomes extremely important. So really quickly on ML infrastructure best practices, designed to execute at scale, repeatability, and efficiently. What I like to call tightly integrated but loosely coupled. Just like in software development, just assume that all these components that I showed in that first chart are going to be plug and play. You need to be thinking how are they programmatically being able to can I replace one and put a new one? These are going to evolve over time. The space is evolving really quickly. So I want to be, let's say, as I said, tightly integrated through API and programmability, but loosely coupled. I should be able to pop in and out of those as I want. Anticipate and allow a variety of tools and technologies to be used concurrently at every step of the lifecycle, and really remain open to integration with a variety of in-house technologies. In a lot of cases, there's going to be a lot of stuff that's developed in-house. You want to go grab the best from open source, potentially, and bringing those in. But actually designing a system where these things can actually be automated and repeatable is extremely important, and that's the framework that should be taken when actually approaching this new software development lifecycle. Some core ML infrastructure components that we recommend: a model registry, comprehensive model catalog, searchable by every data scientist, fully documented with all models running on demand. Connectivity and extensibility, model pipelines and APIs, cloud-based and on-prem data sources, DevOps alerting and monitoring systems, and then integration with third-party tools like Jupyter Notebooks. And some enterprise considerations that are important: infrastructure agnostic deployment. So we see this all the time. Hey, this workload needs to run on premises. This other workload, I want to burst it into the cloud. So thinking about, okay, well, do I really want my data scientists learning 17 different ways of doing this? Or can we approach them with a standardized way of doing this where we abstract the infrastructure from them so that they can do this in a much faster way? Allow for collaboration and pipelining, allow for understanding what performance SLAs are for the different kinds of models and making decisions based on that. Think about regulatory compliance, governance, accounting, chargeback tracking, security, and authentication. And so really quick case study that we did in financial services. So we talk about this machine learning roadmap. If you come to our actual booth, this is completely product agnostic. It's what we call the roadmap to machine learning maturity. You can come in and get a map at our booth, and you can just draw where you think your organization is at the from a data, training, deployment, and management layer, and see where your maturity is, and then understand where you can actually implement things at your organization's level to move that maturity over to the right. And so in this particular case, to give you an example, initial is substantial but incomplete data warehouse, group-specific data science one-offs, manual model and app integration. And where they're trying to go is really improve their data so that they have deployment automation, CI/CD integration, decoupling the apps from the model releases, being able to do ongoing security audits, and expanding on their data lake. So again, it's a journey. Right? You have to start somewhere. So it's just start thinking about these components and how you're going to get the automation. Because at the end of the day, what I showed at that first slide of that iteration, that's what you want to unlock. If you can unlock, if you can allow the data science team to go wild, right? Within the right parameters, you are going to get really, really good results. But you have to give that flexibility so that they can iterate over time. And with that said, I am done. If there's any questions or answers. Any questions? I stunned everybody. Yeah. Yes. I'll absolutely be posting the slides, and also we have actually an 8-piece white paper that explains every stage in a lot more detail. Again, completely product agnostic that you can download and read for yourself. That's available on our website. But if you stop by our booth, we have a bunch of this information as well. So it has multiple parts to it. So if you go to our website, there's like 6 parts to it. But it's overall, it's the state of machine learning is kind of like the survey that we did, and then the white paper explains each stage. Yeah. Yes, so we actually have, in our product, we have a built-in evaluation suite which does performance testing around kind of memory usage and CPU usage and cycles and consumption time, and you can actually build around that tool. It's a tooling, so you can build your own tests. Yeah.
So the models that are supported on this platform, are they like, can we use the Jupyter notebooks also, or is it like a fixed format?
Yeah. So we actually have, our entire platform is programmatically controlled. So if you I always say the same joke. It's like we hired really good designers and they made a really pretty UI, but if you never want to look at it, you don't have to.
So in terms of versioning, I'll be able to understand exactly what changed in the model whenever I'm.
Yeah. So you'll have on the training side, you'll have the versioning on your Jupyter notebook. We don't host the Jupyter notebooks. That's somewhere else. But then from a model perspective, we have a full Git repo that shows all the changes and the builds.
You mentioned during the talk, briefly talked about using Git for model versioning as just a source code, but Git doesn't do well with binary.
Sure. Yeah. So you can use a blob storage that has some sort of like layer. So what we do is we do both. Kind of like the blob storage, kind of like versioning, which could be an S3 or something like Minio on VMware, plus the Git for the query code and the kind of like weights and stuff like that. And so the combination of those two gives you the versions. Correct. Exactly. Great. Well, if there's any other questions, feel free to stop by our booth. I'll be hanging out around there. Thanks for coming today and listening.